listening to Future in Steel, a podcast series about the composite revolution. Brought to you by Tree Composites, winner of the 2025 Chamber of Commerce Innovation Award. Hear how challenges, vision and real-world innovation meet. How leading Dutch companies, innovators and key stakeholders share their vision on the future of industry, steel and manufacturing, strengthening Europe's position as a global economic power in a rapidly shifting geopolitical landscape. Glad you're listening. Europe's ambition to remain an industrial and economic powerhouse depends on its ability to rethink not only energy systems, but also the fundamental technologies behind them. Offshore wind is a prime example. At the heart of it lies a century-old bottleneck, welded steel connections. In this episode of Future in Steel, we speak with Marko Pavlovic, Associate Professor at the TU Delft, co-founder of Tree Composites and inventor of a radically new way of connecting steel structures. Inspired by nature, validated through full-scale testing, his composite steel joints replace complex welds with bonded composite connections that deliver unprecedented fatigue resistance, lower weight, and faster production. Here, how Marko explains how this technology works, why it represents a true breakthrough in connection technology, and how it compares to state-of-the-art welding, going deep into engineering fundamentals and looking ahead to a future where offshore wind structures are lighter, stronger, and built in Europe again. In an in-depth discussion with Future in Steel host Maxime Sevre, CEO of Tree Composites. Marko, on behalf of Maxime, wonderful to have you in Future in Steel. Great.
Thank you.
And may I add, it's a bit of an honor as well, because we're talking to the inventor at the moment. Great to have you.
True.
Yeah,
Thank you.
True.
Yes, Marko, I'm really happy that we have you today. I'm really looking forward to indeed share with the people also about the great journey and all the things that we did. So I think obvious question. Shall we begin on how it all began? Let's say, how did you came up with the whole idea?
Yeah, sure. So, well, as we say, it's inspired by nature. It happened around maybe 15 to 10 years ago when I was simply walking through a park in Belgrade with my young children at the time. And, looking after the children, but also looking a bit around. And I spotted a tree. It's an old platen tree in Belgrade in a very beautiful park next to a museum. So the tree is about 150 years old. And, humans, they notice that tree wants to grow further, that it needs some kind of support. So what they did over the decades, they just placed some metal columns underneath the branches of the tree so the branches can grow further and resist the wind forces, actually. And then, that's the fatigue of wind that now acts upon a tree. Well, what actually happened over the decades, and they were placing these metal columns longer and further away, the tree grew its fibers around the heads of these metal columns in such a natural way and in a way that reduces the stress concentration. At that time, I was also working in structural engineering and then at the faculty in Belgrade, teaching students about steel structures mostly. And I've noticed that how in structures we try to make a very precise and meticulous geometries, and we still end up with problems of fighting a lot of stress concentrations, while tree and the nature actually found that way in an organic manner through an evolution. And that really was placed in my mind at that time. But at that time, I didn't see the problem, that much of a problem yet. Then I came to Netherlands 10 years ago to continue career at TU Delft, again in structural engineering in steel and composite structures. And actually, I shifted a bit my career from being an expert in steel, becoming an expert in composites, the fiberglass and carbon fiber composites. But in this vibrant offshore environment and looking forward society where energy transition is very important, talking to industry, realized, and to my colleagues, how big of a problem connecting the steel tubes with welding is. And then that image from that tree came back to me.
Yeah, because if you just think about indeed 10 years ago, you still had to be quite bold, as in to say, well, welding, we do that always, right?
Yeah.
But suddenly, no, I think this will work, right? And you actually put energy and a drive into it to actually start testing these things. So how did that go?
Well, it went by simply trying. So I had an idea that, well, composites, they are lightweight and flexible and very much fatigue-resistant material, and also fibers. So we can use them to resemble what nature did with natural fibers in a tree, to also build an organic shape around the node where steel tubes meet each other, and to use that whole circumference of the nodal region instead of just a small intersection of steel tubes where welding is possible. So the idea came by, and I spoke to my colleagues, to my professor at the time, and he said, why don't you just try it? So there was a master student actually interested to try this idea together with me, and we thought about how we can actually make it. I made an inquiry throughout Dutch companies dealing with composites. At that time, I was also building my portfolio in composites in Netherlands. And one of the companies was interested in trying to help us to make the specimens, because they made, and they still make, fiberglass pipelines. And they kind of use similar technology to connect fiberglass pipelines, but not for structural purposes. And my idea was, let's go beyond. Let's really try to connect something that is big and has large forces to be transferred.
Yeah.
And these are the offshore structures that suffer a lot of fatigue, actually. Yeah.
Yeah, what pops into my mind is that maybe, can you perhaps also explain, so what is the current difficulty of welding? Why is it such a problem, and why does it need any change?
As I said, when you try to connect steel tubes by welding, you're actually using only a very confined intersection of the tubes. So that's a very limited area where you can apply additional material to connect the tubes. And that results in two major things. One is local stress concentration. So we actually have those tubes that are thin-walled. The ratio of the diameter to thickness in real scale structure is about 50. So it's more or less like a tube of a toilet paper. It's very, you could say, fluffy if you try to press it. So when you try to apply a tube to a tube, you're locally applying a lot of local bending of those walls of tubes, and that creates stress concentrations. Another thing is welding leaves mark in the steel material. So once you weld, the material does not come back the same. There are heat transitions. The temperatures go up to 1.5 thousand degrees or more, and then the cooling rate is important. So that all leads to transitions in the composition of the steel material around the weld, which makes the steel material more brittle around the welding region. That combined leaves a limitation of how much that region where two tubes are connecting can withstand in terms of cyclic repetitive loading before it fails. Yeah. So it's the limitation of space and changes in the material due to temperature.
It's funny, actually, that it has taken such a long time before actually rethinking the idea of creating new connections. At least to me, yeah. I'm not an expert, and by far not an expert, but that's a point. That's funny to say.
I don't know why is that. I mean, structural engineers are really bright people, also mechanical. All engineers are bright people, but sometimes they are really limited by time. They need to work on projects on fast pace. They need to pick up solutions that already exist. And that usually comes up with using a single material that they've been educated and have a lot of experience with. And in this case, it actually the breakthrough was actually in combining materials, in using steel as a basis and then putting composite around it to form the node, the knob, where you can actually transfer a lot more forces. Well, I got an experience of combining materials. Actually, my PhD research was in combination of steel and concrete, where I was investigating really mechanics of how to connect steel and concrete with some demountable connectors. So I was doing experiments. I was doing a lot of numerical simulation. So I already sensed the benefits of combining two materials, and then probably that's how I came to this idea.
And the funny thing is that at the end of the day, a tree got you thinking.
Indeed, the nature, yes.
But it's also funny what you say, is because I think the industry already was noticing by these statements, as in, hey, we need to do something else, right? So the statement that I'm talking about is that, let's say, welders, but also designers say actually the best weld is no weld at all. True. And there was already existing this statement before we even went into composites to transfer, right? So it was already there. But also, and I think that's one of the things which I like about universities, is that they can do, let's say, breakthrough technologies and develop them. Because as you said, if you're an engineer, you need to design something that can work, let's say, in a year from now, or can be built. And if you do something new, then that's not possible.
True, yeah. Well, in my case, it was a combination of engineering and science, and in my earlier career during my PhD research, and when I was living in Belgrade in Serbia, I also did a lot of engineering and consultancy work, designing real structures. So that gave me a perspective of let's do something that actually can be applied, and let's do it in a scientific manner. And in university is really a great place, because also speaking to your colleagues can also help a lot of building up the ideas. Actually, the idea of putting composite around steel tubes already existed, but in a completely different, with a completely different objective. So people were trying to put, and they're still doing that, to put a bit of composite around these nodal regions to strengthen the existing welded joints when they come to trouble of fatigue or corrosion. And I saw that, and I, on the other side, saw the opportunities of composites that I was starting to investigate and to sparkle the research on composites in Delft. So I said, why don't we just put more material around and transfer all the force transfer to the composite and not use weld at all? And I think that idea even came along discussing with my professor, with Professor Milan Veljković. I bounced the idea to him. If we put more composite, we can actually solve this problem of welds. And then I think in the conversation together, we somehow came to maybe we need weld at all.
Yeah, because indeed, one of the things that our listeners also probably don't know is, how does it exactly work?
Oh yes, well that would be good to explain through. So the point is, I said, the problem comes from, if we try to connect steel tubes by welding, we are really limited to a small intersection area of the tube. So it's more or less the cross-section of the smaller tube where you can put the weld. Well, in this case, it's thinking outside of that area. So utilizing the area of the tube beyond that intersection. So using the whole nodal region, wrapping it with a composite material. And in this case, you can imagine the composite material being a very thick layer of glue, and that you splash around, or maybe even you can think of it like wrapping this region with a duct tape. Sometimes you try to fix something in your garden or in your house with a duct tape temporarily. Sometimes it breaks instantly, sometimes it just lasts forever. In this case, we try to make it last forever. So the composite material that is flexible is now joining this whole region of the node in a much larger area. And then the load transfer is not at the direct interface of two steel tubes, but it's actually by bonding the larger area on a smaller tube and bonding to the larger area on the bigger tube.
Yeah. No, I think this is a nice way to explain it. And if we do that, right, so why is it then, what is the result compared to welding?
The result is that we have a lot more a real estate to transfer the load. So you can actually choose the amount of surface that you want to use to transfer the load. And that then actually can result in a design for smaller load levels. You can use a smaller surface for a very large load levels in a structure, in a position in a structure. You can use larger areas. You can make this composite wrapping longer and then transfer more load.
So if I understand correctly, then we can have the steel tube to be consistent, one shape, and then depending on the load level, we can have a tailorable design of the...
Oh, definitely. So people were trying to solve this problem of welding by making steel tubes thicker towards the nodal region, and that's what in industry is called cans. So, for example, a tube of a diameter of a meter would be about 30 millimeters thick in the region between the nodes in the structure, in these lattice structures. And then in the nodal region, it would be increased to 40 or 50 millimeters just to fight this problem of stress concentration and local wall bending and stress concentration related to local bending. While in case of composite joints, we don't have, first of all, we don't have to make this thicker steel in the nodal region. And that also has a snowball effect, because if we don't have this thickness transition between relatively thick steel tube in the nodal region and then call it normal steel tube thickness in the region between the nodes, then omitting this thickness transition already alleviates stress concentrations that are in steel structures also known to be existing for transitions in thickness, because the stresses can actually go straight to the tube. They don't have to deviate through a thickness profile that is varying. Another point is if we can actually completely omit connection between the nodal region and the tube between the nodes and just make the tube straight without any welds entering the nodal region, then we can make those tubes approximately 2 times thinner than they are at the moment.
2 times thinner?
Yes.
That means a lot less material.
That means a lot less steel material. It actually means that if you want to build one support structure for a turbine offshore, based on these lattice
offshore
structures,
wind, yeah.
offshore wind, we can make 2 structures out of the material that so far we could make only 1 structure.
A reduction of 50%. That's incredible, Maxime.
I know, this is one of the reasons why.
Well, but apart from that,
why I'm so enthusiastic about
less material means less CO2, less anything.
Exactly, less transportation.
And please explain. But the amount of the time that it can last exponentially goes up, because this connection lives forever, as far as I know.
Well, that's another point of the composite material. It's quite durable compared to steel. Well, we all know steel corrodes, and corrosion, in one way, it reduces the material in the structure. So you have less material to govern the forces, and you have more stresses. But it also creates a very, on a micro level, stress concentration, which additionally punishes the fatigue performance of steel and welded structures. Well, composite does not rust. We are actually dealing with material that is already used for a lot of marine structures. Boats are made of composites as well. And when it comes to mechanical resistance, well, those turbine blades that are in the turbines, in wind, offshore or onshore, they're actually made of composite. And they tried in the beginning of era of wind energy to make them from aluminium, but that was more or less a disaster because they were constantly failing due to fatigue. Okay. So the turbine blades, those things that spin all the time, they suffer a lot of fatigue loading. They are actually made of composite because it is fatigue resistance. It is fatigue-resistant material, and for blades, it's also important that it's lightweight. But for our application, the lightweight character is not so important. The durability and fatigue resistance is important for us.
Yeah.
Wow.
So it means indeed that it can be lighter, and then where we are now limited in lifetime by the welds, because they more or less dictate how long you can have a structure survive in the marine environment. Suddenly, that weld is no longer, let's say, determining the lifetime, and we could go to much longer lifetime with less steel, which is, let's say, for the longer run for society also interesting, because then we have to put one, let's say, foundation out there, and we can have, let's say, instead of 35 years, 70 or more.
Yeah.
And that's something that I think we really see as, okay, this is a breakthrough. However, indeed, breakthroughs go slow.
Yes, but this is developed or rethought or invented, so if you will, with regard to offshore wind.
Yes.
But the sky is the limit with regard to all other applications of steel, I guess. Marko.
True. Yeah. All larger scale or smaller scale structures that rely on this lattice type of and truss type of structural bridges.
Yeah.
Maybe even stadium roofs. There are other offshore structures for marine farming or cranes, for example, offshore or onshore. Any type of structure that is made of tubes in this lattice form and that suffers dominantly fatigue loading, that is repetitive loading over time, can really have a lot of benefits from this.
Does this mean that, and I'm not trying to overstate, but does this really underline why this means a composite revolution, Maxime?
Of course. No, it's indeed. So we, if you look at the application fields, they are, well, gigantic. As in, okay, you can apply it in many cases. At the same time, we also see, okay, where do we actually face the biggest challenges when it comes to welding and lifetime, and that's actually really this offshore wind. Let's say, or actually offshore structures in general, where you have waves continuously slamming into the structures, really imposing high fatigue loading. So it is really tough for these structures to survive. And that's why, okay, you have to add so many additional material such that you can connect those and still have the same lifetime.
Could you say that if you apply it there and it works over there, it will basically work anywhere?
I think it's one of the heaviest loaded fields. Yeah, so if it works there, then of course it will work also in all the other civil structures, and there are many. And I think one of the things that I was about to ask is, you're also part of a whole committee, right, on behalf of the Netherlands. Can you tell something about that? Because I think that relates also to the wider application of composites in civil structures.
Indeed. So coming 10 years ago to Delft, I reshifted my expertise to composites. And over time, I was successful in supporting development of that material nationwide, but also Europe-wide. So I'm part of the I'm one of the representatives of Netherlands in a European Committee for developing European codes for design of structures and for other types of structures, for steel, concrete, timber, groundwork, and so on. There are already so-called Eurocodes that define how we can design and how we need to validate structural integrity and safety. For composites, it didn't exist. So for composites, it's being built now, and I'm part of the European team doing that. So putting the expertise of composites into the design codes of future.
Wow.
Yeah, because this is also one of the questions that I remember, let's say 5 years ago, we were talking to Wouter, I don't know if you remember, and he said, yeah, it works. So why do you need so many years before it's actually applied?
Well, construction industry is quite a conservative industry, and for a good cause, I would like to say, because it's really about safety, it's about human lives, it's about the safety of our infrastructure and reliability of our infrastructure. So for good reason and understanding, I acknowledge that our field is quite conservative, which is good for reliability, but it's really tough and really thick medium that you have to go through to push innovations.
Yeah.
So what did we do, right? Because let's say 8 years ago we saw that it was working. So why couldn't we apply?
So what we did, we sit down and wrote a program. What all needs to be proven to show from mechanical and perspective how this technology is reliable. So we wrote a program, and now we are at the end of the second stage of a very large research project. Funded by Dutch government by RVO. We call those projects RapNode projects. And actually today, after recording this podcast, we are going to go to Schiedam and to do a very large scale test. It's probably one of the largest scale tests that I've organized so far in my career. We're going to test a scale down of a jacket structure that is 1:5 scale, which is built with composite joints. So composite joints were fabricated and then put together with steel tubes to form a structure. And today we're going to do the ultimate load test. We are actually going to go to 150% of the design load.
150%?
Yes,
okay.
So 50% more than the design load, to prove that actually these joints can withstand that in a structure, not only as components, but as in a structure. But there is one small thing in the whole program of testing that we have done so far, where we went in several different directions of proving that it works for different conditions. And that means we first tested at a laboratory scale, which is nodes of this size that I'm showing now, but the real thing, the joints and nodes in these offshore jacket structures are actually a couple of meters large. So we have tubes of about 1 meter, the smaller tubes of a diameter of 1 meter, meeting tubes of 2 meters in diameter approximately. So if you imagine a K-shaped or X-shaped node over there, it's going to be 3 by 4, 5 by 5 meters in total magnitude. So to prove that this bonding technology that actually transfers the load, the bonding is what transfers the load between two tubes, can work in an upscaling manner, and to prove that the scale effects, we know that the scale effects exist in mechanics, but to show that we can know how they develop when we grew in scale, and that we show that we can, to build up the models, that we can predict in different scales how the performance will be, we had to do a lot of tests. So we did laboratory scale tests in Delft, in Stevin 2 lab in TU Delft, of two scales, 2 sizes. Let's call it S, M, and L, like the shirt
like
sizes
the shirts,
or whatever.
Yeah.
So we did M and L actually in Delft, and what we did in XL, we did in OCAS in Belgium.
Okay.
So Mark, director of OCAS, is also going to be
is a guest on another podcast.
Yes, so he'll talk more about it. But we went to them for 2 reasons. First of all, they had a bigger machine to break things. So we are limited in Delft with capacity to 10 meganewtons.
Mm-hmm.
That's 1,000 tons capacity to break things. So we used that to test the L node, which is of 3 meters long. But then we went to OCAS, to Belgium, to test something that goes to 1,500 tons to break it. And that's where we actually went up to scale of the full-scale structure. And we were able to resist loads that are much higher than actually needed for static resistance, for storm conditions. And then for fatigue loading, we saw tremendous increase in the amount of cycles that this technology can withstand compared to
So basically
welded.
all the tests that you have run actually tell you that this is working.
Indeed, and
Sure.
I think we're quite modest here. In at least that's how I experience it now, because it is 5 years now of really intensive amount of testing. So it's not only about. So why was it so important to have this full scale validation?
It is important that we can build a data for us, an understanding how this technology works, how bonding holds the forces, at which level it will initiate some cracks, how quickly those cracks will grow, and by that we can build design recommendations and we can build prediction models. So we're actually using quite sophisticated computer simulations, like maybe for our listeners, we all look into the weather forecast every morning, or we're looking at it for tomorrow. So what we are actually doing in structural engineering and in mechanics, based on some experimental evidence, is we are building up the forecast models of how the joints will behave in the real conditions. And that's why we had to do so many tests to support our simulation.
And I'm right that we are, let's say, doing all these tests such that we can understand how something would break, such that we can prevent it.
True.
Right?
So we always break things, but we
but that's a funny thing. You try to break things.
Yes, because for us as engineers, that's very logical. But and I think that's also what I meant is that 7 years ago we saw that it worked, but then will it work also if it's a little bit bigger? If we put it into sea, whether it's snowing, whether it's freezing, all these questions you need to be able to answer. Not just saying, "Hey, trust me on my blue eyes."
No, you have to prove it.
No, you have to be able to understand it even, right? I don't, because if I prove it by one test, you say, okay, this is one test. But now if you make it 2 times bigger, will it work?
Well,
so, and I think that's also really something that you have to understand, that the test that we do, it's not only you test it, no, you measure really a lot. We measure on the outside, on the inside. We do all kinds of measurements to be able to actually show that we understand what we predict.
Yes, we use state-of-the-art
really
techniques.
High reliability.
But that does not mean, and that's for clarity, it does not mean that you in any way doubt the possibilities with regard to
No.
composite or
No.
composite joint? No,
No, not at all.
You're just validating everything in all kinds of conditions.
I think, as Mark already mentioned, reliability in civil structures is key, right? So if we have any doubt, we will not put it out there, right?
No.
So
And that's good.
Well,
and
I'd like to-
just with the floater that we made, we already showed that we can survive storms. So in 2023, we actually put the technology
You put a
already,
big structure out there, right?
including also having embedded fibers inside that would track, let's say, the performance over time.
Yeah, we're using a lot of those measurement techniques, and they are all state of the art. For example, today we're going to use a combination of optical fibers that are embedded inside the composite next to the interface with steel. So it's the same type of optical fibers that we're using in our homes for internet, but we use it with a specific type of equipment that we can measure straining and stressing inside a composite material. So it's like nerves in your body. We can actually feel where it hurts. And we are using stereo cameras with specific patterns on the surface to notice if there are any cracks and when do they appear. We're using lasers to measure the formations of structures, and all that comes into a computer system which we then use to compare to our simulations, where we are like a digital twin, where we are also replicating all these conditions such that we become able to predict all different geometries of different load cases on different sizes. Yeah.
Wow. On a scale from 1 to 10, where are we at the moment in terms of, the testing all the facilities and testing? Where are we at the moment, just for the listeners?
I would say for testing and understanding how it works and proving how it works, I would say 9. It's not the TRL level that we are talking here
Exactly.
now. The TRL
That's
is also
what
application and proving in a real environment. But with knowledge about it, we are at almost at level 9, I would say.
Yeah. I think we can strongly say that we truly understand what is going on, and that we have reliable prediction models that will work in all the conditions that we have. Then maybe a question that we also sometimes get is, how do these compare to alternatives of welding that are existing, like casted welds? Casted joints.
Casted joints, yes.
Yeah.
Well, people already thought a long time ago that a more smooth shape of the geometry in the nodal region could help to reduce stress concentrations. That's how what is called casted joints came to place. So, and they got a name by really the production process. So you would build a huge mold, and then the nodes will be shaped again, made of steel in a smooth manner to reduce these stress concentrations, and then you will create nodes that at the end would be welded to steel tubes. Comparing it to composite joints, I would say composite joints that we are developing are a resemblance of casted joints in terms of using this organic shape to reduce stress concentrations, but they don't require mold to be made. For casted joints, every casted joint needs a very expensive and complicated mold. And at the end, the casted joint still has to be welded to the rest of the tubes. With composite joints, we can omit that if we want and when we want it. And then the casting is a difficult process of controlling the quality of the cast itself. So there are a lot of problems of having acceptable level of porosity and toughness of the material at the end. So in that respect, composite joints outperform in manufacturability and connectivity to the structure, and also can in reliability level as well.
And last but not least, this can be manufactured in Europe.
Yes, and I think also at scale. Casted joints, they would, if you look at offshore wind, it's not one structure, it's like 50, right? So you need to also have this enormous volume to be produced. And I think the composite joint can be made with fully sourced materials from Europe, but also by manufacturers in Europe, because we just have a more, a simple way of making it, where in terms of welding, right, you heard how prone it is to fatigue. So all quality checks need to be so really thorough, right? There cannot be a single error, because it would deteriorate the lifetime tremendously. And now suddenly we have an entire, let's say, a volume which transfers the load. So if there's anything which would be, let's say, not completely to spec, it's much less sensitive to it. So it's very, in engineering terms, we would say damage tolerant, right? So, and it doesn't fail if you have a single crack. It doesn't filter. This is exactly what composites do, right? So we know that there will be imperfections, but we actually know how they build.
Yeah.
So if you compare it to, let's say, airplane wings, most people don't know that they are full of cracks.
Yeah, made of composites also.
But we know how fast they grow because this is very predictable, very reliable. But indeed, when you would compare, if it would be a steel wing, we would be scared because we don't know whether it will get to the other side in the next flight.
Yeah.
And there is fundamental difference between how composites and how steel responds to cyclic loading. Steel would take relatively long time to initiate a crack. And then once one small crack is initiated, then the growth of that crack around the whole structural detail can be very quick and therefore unpredictable. Well, with composites, the crack initiates very early, micro cracks initiate very early. We have some softening on the material. It's really a flexible material. It creates a bit of relief where it's needed. And then those micro cracks, they grow in volume, but in a very stable manner, and we can predict that.
Yeah.
So we can rely on a damage tolerant design.
And the funny thing is, we called this podcast series Future in Steel. That's because of this.
Yeah.
This is the future in steel, isn't it, Marko?
Yeah, using combinations that can solve the benefits of both worlds. Well, why steel? Well, steel is a marvelous material because it offers so much stiffness and strength for a certain amount of weight and for a certain amount of effort to get to that material. Now, we do have a steel industry well developed in the world. So steel is going to be there and stay there. There is a definitely future in steel, but we have to think about complementary technologies that can make it grow better.
Yeah. Wow. Maxime?
Yeah, yes.
Even I understood what this is all about.
Exactly. So I'm very proud to do this together with you, Marko, and I'm really looking forward to taking the next step and really placing offshore structures with composite joints there. Yeah,
true pleasure.
And for me, thank you very, very much to you taking the time, Marko, to explain to laymen like me how this all works, because I truly understand now how it works. But furthermore, I understand even more that this is the future in putting steel constructions together.
Yep.
It's as simple as that. The future in steel.
Definitely.
Thank you very much.
Thank you.
Thank you.
You have been listening to Future in Steel, a glimpse into Europe's industrial future, with thanks to Marko Pavlovic and Maxime Severe. And if you want to know how your company can benefit from the composite revolution, or if you are interested in becoming part of this development, don't hesitate to contact Tree Composites. They'll be happy to be of assistance. And for now, my name is Koos Woltjes, and see you in the next Future in Steel. You have been listening to The Future in Steel, a podcast series about the composite revolution, brought to you by Tree Composites, winner of the 2025 Chamber of Commerce Innovation Award. If you haven't already, please subscribe to this series on your favorite podcast platform, or visit the Tree Composite website for additional resources. Thank you again for listening, and we look forward to bringing you more insight in The Future in Steel.